and say welcome everybody to day 4. We made it to day 4. I am very sick. I'm so glad we're meeting via Zoom, so you don't have to share my germs because this is not fun. I think it's a cold. I do not think I have COVID at all. I've been coming down with this cold for a week, but so day 4. Before we, it's a great question about data. Let's look at our Canvas right now. So, okay. This is kind of my email that I'm going to, no, this isn't the email. This is the email. No, I thought I had the email brought up. I'm going to be sending an email out at the end of class. Let's go to the syllabus. That's a good spot to go. Oh, I need to share my screen so you guys can see it. Yes. Okay, so I'm going to go to Canvas. So I've gone to the syllabus section of our course website, Canvas page. So today is the 10th, so there's nothing due today. What is going to be due next time we meet on Tuesday is a discussion on doing homework 1 and homework 1 itself. I'm going to have those 2 things due. You should also be doing the week 3 reading preparation. I have bumped it due to the 17th because I didn't want to overwhelm you too much over the weekend. But we're going to go over the homework 1, type what it requires you to do. It requires you to do multiple linear regression in R. The homework, if you click on the homework, it tells you here are the files you need to download. Here is the encyclopedia link that can guide you through using R. This is also what we're doing today. So this is something I don't think I pointed out before. The homework, this directions file is the skeleton is the RMD file that you type into. The directions file is this RMD skeleton knitted to PDF, but I changed its name to direction so that you don't save over it on your own computer. So it's the knitted blank RMD, the skeleton RMD, so it's easier to read because reading in the RMD is sometimes harder to do because of all the markup. To run this RMD, you need the same APA7 CSL formatting the style file, and you also need this .bib file. This is a different .bib file than the one we used on homework 0, which has been graded. Everyone seemed to do great on that. So let me just open this just to give you a brief view. So this is the PDF that's called Directions, and this is for our next homework that you're going to be working on up until next Tuesday. So it has a table of contents, and Alejandro, this is for you. You commented that it was hard in the last homework 0 to find where you were supposed to type in. I used to use a special package, and it made like highlighted boxes of different colors, so you knew you needed to type in all the yellow boxes, but that package is broken, and I've tried to use other ones like it, and it tends to be more of a headache than they're worth. So on this table of contents, it has things listed as prompts and to-dos. So the prompts is where I'm asking you to type, and the to-do is where you have to type something in a code chunk. Yeah, we like this, right? So there's not a lot of guesswork. You can see what you're supposed to be working on. All right. So, and you can always email me if you have confusion. So you can click on here, you see the page. Now these page numbers are for the blank skeleton before you work on it. Again, this is the one that's named as directions. So Psych 7650, homework 1, directions, because it's the knitted one. So you're going to do exploratory data analysis and linear regression on this data set called Beat the Blues. So the first part of this document introduces you to the Beat the Blues data set. So it tells you this is where we get it. And so the first thing is install this package on CRAN. I think I missed this one before. So you have to go to the packages tab, the install button, and get this package. It's named after Handbook for Statistical Analysis Using R. And so that's where this abbreviation, huzzah, comes from. And then it tells you the variables in the data set, how to load the data set, and then here's some basic descriptives. And so then prompt to do 2. You're supposed to create a table like the one above, splitting it by variable, and then here's a prompt. So make some observations comparing the pattern of this Beck depression inventory score over time between the two groups based on that descriptive table you did. So this is what we're going to learn how to do today on an example data set in class. I will also tonight be making another more involved walkthrough and posting that as well. But based on what we do in class today in the encyclopedia, you should be able to complete homework 1 here. So this is homework 1 that's due on Tuesday. So the other thing that's due on Tuesday is a discussion board about how it went on homework 1. So post any questions, concerns about the R code, about the content, about multiple regression, errors you get, answer each other's questions. I will be on there this weekend and Monday and Tuesday so that we can get everyone through homework 1, because next week we want to do multi-level modeling, right? That's the whole reason we're here. So we got to get single level regression caught up on. So that's what these two are due on Tuesday. So the next set of reading is not due. I haven't marked it due till Thursday, but please try to do it before Tuesday's class. So Tuesday's class will be more meaningful. Tuesday will be more of a lecture day. A little bit more. Thursday will be all application. So the required reading for the next week is Hawkes chapter 2. It's a very readable chapter. He goes through an example in here. We will actually be doing the example in class. So I'll show you how to do those things that he says, when you do this, you get this. And he makes a beautiful table. I'll show you how you do it actually in R. And then we'll talk through the example. But please read chapter 2 of Hawkes. I've put this first HLM video. It's HLM 1. This is a set of 4 videos. You only need to watch the first 23 minutes. About the 23-minute mark, they change over to talking about multi-level modeling within the SEM framework with latent variables, which some of you, that might be intriguing. You're welcome to watch the whole thing, but you only need to really watch about the first 22, 23 minutes of it till it hits that SEM part. There is an optional textbook photocopy in here, but it does code in SPSS and SAS. Ignore that, and you can read, especially the first, I don't know, 6-8 pages are good to briefly review. It goes over a lot of the same material Hawkes does, but sometimes reading it in a couple different people's point of view can help different things pop out to you better. So again, that's the material we're going to cover next Tuesday and Thursday of next week. So really getting into basic 2-level, multi-level modeling, specifically in hierarchical or clustered situations, not longitudinal yet. We'll get there, but not yet. Okay, so questions on what you need to be doing after class today and through next week. We good? Homework 3 for next week is already up. You can go ahead and get started if you want. I got to make sure that I've got all these dates right. Homework 3 right here is you are going to search for journal articles in your field that are multi-level and find and turn in one that's hierarchical and one that's longitudinal. The details are in the homework 3 file that's linked here if you click on the assignment homework 3. And you can definitely email me and use the discussion board if you have any questions on that. But that's kind of a forward of what's going to happen next week. So that's where we are at now. We know where we're going. Okay, so to R we go. Does anyone have any questions before we get started in R with multiple linear regression, single level regression? See everyone's faces for a second. Anyone? Okay, today is going to be more of a lab. I could take 5 hours to teach you all the things you can do with multiple linear regression in R, but that would be, you've already taken a course in that. So this is just a refresher. This is basics. I'm going to show you the things that I need you to know and be comfortable with. Betas, how to interpret betas, and interactions between continuous and continuous variables, continuous and categorical with categorical. How to get predictions, how to get simple slopes, and how to do plots, as well as make a table of the model. Those are I have my little list of things that we need to get down so that we can understand in single level, so that when we go to multi-level modeling next week, we don't get like blown away even more than we're already going to be. So please, you have my permission to interrupt me as much as you need. Whatever we don't finish, I'll make a recording on and upload it. I've got some basics I want to hit, but really I want to get, I know a lot of you have done some regression, a lot of you have not done it in R, and a lot of you it's been a long time. So this is your chance to ask the dumb questions about what this means, how do I interpret it, how do I actually do it. You guys promise to ask questions? Okay. Did everyone get the announcement with the RMD walkthrough for today in class? It's called Regression Walkthrough Interactions 2020. We good? Okay, I'm gonna shrink down the picture part because I gotta see my, let's see. I'm gonna shrink down to where I just see mostly just my notebook, the source part of my R. So this is for our in-class conversation. This is the Latex Engine that helps some Mac. For whatever reason, Macs sometimes, and even Windows work better if we add in this Latex Engine. Don't know what it does. This adds some code highlighting. Yes, we're going to do a table of contents, but only 2 layers deep, and we're not going to number it. And this is reading in some LaTeX packages that we may or may not use. I am a really big proponent of not recreating the wheel, so I usually just copy and paste from one file to the next. So these are things that I find helpful in general. Even if I'm not using it on this project, I'll probably put them there. So for today, we're going to need 2 packages to be active in R. We need the tidyverse, which actually activates 8 packages, and then EM means. EM means stands for estimated marginal means. It's going to be real. And I guess let's add library. Let's add furniture. That's Tyson's package for making summary tables. And one called Tech, T-E-X, Reg, R-E-G. So all 4 of these packages we installed when we did our big package install. They were all on that big long list. So I'm gonna activate all those. So here are the 8 packages that tidyverse gives us. Okay, so this example is coming from the UCLA website. They have great stuff on their website. So here's a link if you want to go read more about it. We're going to be looking at using as our example data set some data that was from a weight loss program. So in this data set, we have loss. These are our variables we have. The first one is loss, and this is number of pounds lost is a positive number, negative is a gain, because in the weight loss program, they don't want you to gain. Anyway, that's how they did it. It's number of pounds. Then hours is how many hours spent exercising, and I want to say this is a week. And then how much effort, I guess they had the people rank how much effort, and this is a number between 0 and 50, so it's also continuous. The program, so they randomized all these participants for a different exercise program or non-exercise. They were on a jogging program, a swimming program, or a reading program. Anyone want to guess how weight loss went in the reading program compared to the other 2? And then we have the gender. They had equal men and women. So the gender variable is binary because there are 2 categories, male and female, for this example, just for this example. And the program is a categorical variable with 3 levels, a factor with 3 distinct categories of no particular order. Although we might speculate the order where we're going to have more or less weight gained. So there's some definitions here. I just copied from their page. Let's go right to it. So at the bottom of what you have in your file right now is read.csv. You can use read.csv to read a CSV file that's not on your computer, that's on a website. So we can run this chunk and it's going to go to this website, the UCLA website, and go get their data set and bring it down. Now, when you run that code, you will see down in your environment, wherever your environment lives, mine's down here. I can't get it to expand because I keep, anyway, it's there. So we can look at it. Oh no, there's an echo. Can you guys hear the echo?
Yes.
Okay, so we can type the name of the data set and run that chunk, and it will print it out for us. So here we've got our ID variable, how many pounds they lost, how many hours they're exercising, the effort they're putting into their program, their gender, and the program. Now, this was a CSV, so notice the gender variable. We can also ask using the Tibble package. Now, let me say this. I am recording this, and I will post it on YouTube tonight, and hopefully it'll be processed by tonight. And I will also be sending, saving this file when I'm done and sending it out in the announcement after class, the class wrap up. So if you don't want to type all this, you can just watch. If you get behind, you can pick it up later. So we do have ground to cover, so I don't want to go super slow, but I don't want anyone to be panicking because you didn't get something, okay? You can't stop me though. So the Tibble package, the glimpse function is a nice way to look at your data set. And we can see that that gender variable, it is being treated as an integer, and the gender and the program variable both are being treated as integers. Are they integers? No, they're number values for categories. So the first thing I probably want to do is take my raw data set and convert the gender and the program variable to factors. This is part of wrangling your data, or cleaning it, or prepping it, whatever you're I call it wrangling. So I use the dplyr package, mutate function, and that creates a new column, and you can create a new column and save it over itself. So the gender variable, I am going to make a factor version of itself, and that's how we write the code. Now I'm using a pipe to connect steps, so I want to do that again, dplyr mutate, spelled correctly, and I want to take that program variable and make a factor version of itself and save it over itself. Now I'm also going to do this on the ID variable, because ID, I don't want it to do the average of the ID. So it's a label, it's not a numeric value. It should not be treated as a numeric value in summaries. So I'm doing 3 separate mutate steps for the 3 variables I wanted to be treated not as numeric, but as categorical variables. So I'm saying treat these as factors. Now, if I run that chunk, I get the data set, and notice it now says factor and program and ID, they're all factors, but notice gender. It's still 1s and eventually 2s. Program variable is still 1s, 2s, 3s. I need to attach the labels to that. Not just say that it's a factor variable, but that 1 means they are a, what did they say? 1 is a male and 2 is a female. 1 is jogging, 2 is swimming, 3 is reading. I need to attach the labels. So the best way, and this is part of the data wrangling that I'm going to try to weave through this class, because we don't have a class on data wrangling. Nobody has a class on data wrangling. You're just supposed to know this stuff. So I'm trying to throw it in. So in gender, after I've said make gender the factor version of gender, I'm going to put a pipe inside that parentheses, and I'm going to use the 4cats package FCT recode. And now I've got this code autocomplete. It tells me recode, that FCT underscore recode changes factor levels by hand. So I'm going to put this in the way you do it. I would say male is my label that instead of the 1s, and female is my text label instead of just being 2 that already is existing. Questions? I know some of you have seen this, some of you have not. Okay, so let's do the same thing with program. So after I make program a factor, I'm going to make a pipe to make another step connected. Again, the 4cats for categorical variables package, FCT underscore recode, factor recode. And on this one, I have to do another parentheses, is the jogging is the text label that should be attached to 1. swimming is the text label for number 2, and reading is the text label for number 3. Oh, now I'm probably gonna get an error. Can anyone find my mistake?
Missing quotation marks on the final 3.
On the final number 3, there are no quotation marks. If you don't put quotes, it thinks it's an actual number value. And so it's probably going to throw, yep, I got an error. And see, there's 3. It wants that to be quoted. Now, the key in R is different in Word. If you highlight the part you want quoted, so I've highlighted the 3, and if I push my quote key, and I'm using shift with the quote key to do the double, it will make the quotes at the beginning and the end at the same time. Kind of handy. Okay, now I'm going to run that again. It should run this time. I hit it 2 times and it got mad at me. Now it's going to
It's very cheap.
okay.
Oh.
I'm thinking.
Syllable of the category rather. Allows us to look at code in lines rather than have it all nested.
Same as like Michael said, it connects multiple functions, so you can just run it.
Going to the next one.
Yes.
Okay, interesting. So that connects all that. Okay. Thank you.
You're welcome. You good, Sarah?
I'm trying to close everything down that I don't need on my computer because my computer is just overwhelmed.
You don't open it.
Really? Okay. It does a It says I have low system resources. Okay, I'm gonna leave the meeting and come back just a second. Like, seriously.
Okay.
Oh. Is it recording? Does it say recording anywhere? I don't see it.
Yes.
Okay, yes, we're recording now. Okay, so when I do these factor relabeling or recoding, making the variables factors and attaching the labels to the categories, you have to save it as a new name or else you're not going to have those to use. It's kind of a very important but often overlooked thing when you're first learning R. So I have 2 different versions of this data set. The raw one is just as I imported it from online, and the clean one is the one that I've done stuff to. If I come up here, I can put a new chunk, and again, the new chunk, you can go Insert R. The shortcut on the keyboard is Control-Shift-M. Control-Shift-M is make a pipe. It's Control, what is it? Oh, I forget because it's just muscle memory. Control-Alt-I on the Windows will insert, I for insert. And it's Control-Alt-I, and on Mac, I think it's Command-Alt-I, is that right? Try it out, Mac people.
We don't have an alt, so probably Option.
Option, yeah, that's what it is. Command-Option-I. So I can ask for the summary of data raw. If I ask for the summary, notice what it's doing with gender and prog. It's treating them as numbers and it's giving us a median and a mean. That's not very meaningful for a categorical variable. But I can copy that same code and using the summary, but do it for data clean. And now data clean for gender and prog, notice it's giving us frequencies of the categories, more meaningful. So we can see that we have 900 people in the sample, half are men, half are women, and there's an equal division of the 900 into jogging, swimming, and reading, because this was a randomized trial. They could do that. And then here we can see the descriptive statistics of our 3 continuous variables: weight loss, hours doing their thing that they were assigned to, and their effort rating. Okay.
Hey, Sarah.
Yes.
So this gives us the frequencies. How would we get like the percentages? Like, so male and female, it's 50-50, but how would we get those?
So the next thing, what we've done right now so far is just read in our data and wrangled or prepared it. The next thing you're going to always want to do is exploratory data analysis. So the first one that we're going to do is summary statistics. So you always want to get, usually we call it table 1. We want to get some basic counts and percentages or means and standard deviations. So this gives us some, but the best one I found is the furniture package table 1 function. So the way it works is we're going to take our clean data, and to that we're going to pipe on the furniture package, and the function is table 1. Tyson named it table 1 because usually the first table in every manuscript is descriptive statistics. So I can say all the variable names. Well, if I don't even say anything, let's see what it does by default. Every function has default. So I'm just taking my data and throwing it into this table 1. I'm going to push my play button. Oh my gosh, we get ID. ID is not meaningful. We don't want ID. So I'm going to remove that variable. And one way you can do that is with the select command. The dplyr package function select chooses variables. So we can unchoose a variable or deselect a variable by putting a minus in front of it. Now let's try that. I automatically know I don't need to do frequencies and descriptives on the ID variable. Okay, so what it's done is it does the mean and the S standard deviation if it's a continuous variable, and it does counts and percentages if it's a categorical variable. Automatically detects that. So for the loss variable, average is 10. Hours, the average is 2. Effort, the average is almost 30. Gender, male and female, 450, 300%. Now it's running out of room, and you can scroll down, or you can put output equals mark down. Oh, I spelled that wrong. Spelling, it's important. And this just makes it a little easier to read on screen. So now we've got count breakdown and percentage as a percentage. Now this is nice. We're getting somewhere. Frequently, how do you see these tables though? What's another thing we see in these tables? Instead of just everyone all in one column, we often see them in separate columns. What's a variable we might want to make separate columns by?
Condition.
By condition. So the way you do that is I would come up here and add a step, and this is a step in our pipeline. You can think of the pipeline like a paragraph, and a paragraph is made up of sentences, one after the other. So our pipeline here has one step at a time, and the pipes are what connect our steps. So we're taking our data set, and to that we are going to do deselecting the ID variable, and to that we are going to do, the pipe says next step is, we are going to group our data by a new variable, and the variable we're going to group by is prog. That's the program they were assigned to. And this is why, one of the reasons the pipeline's nice, you just add a step in between and run it. We don't have to look inside the parentheses and find the innermost parentheses. Okay, so now notice our table. What do we now have? We have means and standard deviations for our continuous variables by group. We have the gender breakdown by group. Now, what if you also want a total column? You can say total equals true, and it will add a column at the front that's for everyone all together, and then it will have the separate programs broken out. Anyone ever tried to do that in SPSS? You have to run like 7 different things to get all that information. Now, some things that are nice to do here, sometimes we want more decimal places. You can say digits equal, let's go to 2. I'm going to scroll down so you can see that here.
Sarah, your audio is going like in and out of crackling again.
Gosh, I'm sorry. No one else is on my internet. I don't know why it's being so funky.
What's the difference between the commas then and the pipes? Those commas are like within the conditions of that specific function, or?
Yeah, commas separate pieces inside parentheses. So inside of a set of parentheses, The commas separate the options, but the pipes separate the steps.
Mhm. And so the way it looks, like the way it's like you hit the enter sign and it drops down to the next line, is that just how you like to see it, or could that still be in one long line just separated by those symbols? Would it make a
These
difference?
are great questions. I could have all of this code on one line.
Oh, good. Okay.
It doesn't matter to the computer. Space is space to the computer. 1 space, 10 spaces, an enter, 5 enters, it doesn't matter. There is some accepted alignment to code to make it more humanly viewable. And here's a trick for you people that have used R for a while. If you want to get it all aligned nice, you can highlight all the code you're working on. So this whole code chunk, and I moved it. Okay, are we back here? And then push Control or Command with the I. I for indent. Let's see.
Sarah, are you still there?
I am. I'm going to try stopping my video.
Okay.
Okay, let's see if my sound picks up or settles down now without the video.
So far, so good.
Okay, so I'll repeat what I said right before. Having things line up can be seen as something that's just OCD, but it can help you pick up mistakes, because if you push the enter key, it doesn't know you've forgotten a comma or parentheses. So that means check to make sure you're having something nice. I think I'm viewing your video. You'll need to use your audio. I think that maybe having all those video streams coming in might be problematic. Let's try this. Okay, so.
We could also all stop our videos.
I think we should try it.
Yeah.
Let's go on to doing some regression, shall we? Okay. Now, I can't see you. So unless you say something, I don't know you're still there. So please jump in. The command for fitting regression in R is LM. And it's in base R, so I don't need to say what package it is. LM stands for linear model. And after you say LM, I want a linear model, you need to say the formula and the data set that it needs to fit the model to. So let's see, I'm going to start the chat up on my screen so we can use that, or show it in my screen. There you go. Okay. Am I back? There. Okay, so LM for a linear model. For the formula, let's model the amount of weight lost. So that's the loss variable, and we want to see if it matters. Let's do a continuous variable. Let's say hours. If the amount of hours that you exercise is predictive of how much weight you lose. And then you have to say which data set we're going to use. It's data_clean is the name. When we fit a model, it's always, yes.
Why don't we do data clean up above, like before you put LM? Why would you put it down there?
You can do both ways.
Oh, okay.
Yes. So I'm going to do it this way first and then show you. I'm doing it this way because of how it's going to interface next week with multi-level modeling.
Gotcha.
So right now we're using the command LM for a linear model. Next week we're going to use LMER for linear model, or linear multi-level regression, the 4th edition. So we'll just change out the word, but the rest of it will remain the same. For the formula, you put your dependent variable first, that's your Y variable, and then you use the tilde wave that's on the key with the back tick up by your escape and tab key in your upper left-hand corner of your keyboard. That tilde away means is predicted by, is how you read it. So we're going to do a linear model where the weight loss is predicted by the number of hours someone exercises or does their program. And we're going to use the data set data clean. If I run that much, it's going to run the regression model and it's going to give me some limited output. And it's very hard to do anything next with this linear model, like plot it and do predictions and do simple slope analysis and estimated marginal means. So what we are going to do when we fit a model, and this is again for single level regression, multi-level regression, I do the same thing with ANOVA, is we need to save it as a name. And kind of you can name this Fred, you could name it Bob, but we're going to name this something that's a little more meaningful. I'm going to call it fit underscore LM underscore loss underscore HRS. Again, you can name it anything you want, but I want to know that this name houses the fitted linear model where I predict weight loss from hours worked. And I can use where I highlight it all and do Control I to indent it all nice. So now when I run this, it will not produce any output because I've saved it as a name rather than asking for some output. Now, how do I get my little, this is in the way. Show all panes. Okay. So now if we look down here in our global environment at the bottom, can you see where it now says fit LM loss hours? So when I ran that chunk, it didn't produce any output underneath the chunk, but it is known in the brain of R, in the global environment. And you can ask for it back, I'm going to insert a chunk, by its name. So I'm just going to take that name, copy it, and throw it in another code chunk. If I ask for the name of the model, it will again give me that very basic output. If I want what we're used to seeing in output for regression, I can surround that name with the command summary. And this gives what we're more used to seeing for a regression output. Okay, so this is the part where we're going to talk about how to interpret betas. So betas are the parameter estimates for each predictor. In this model, this is a simple linear regression. We only have one predictor, and that's hours. So the beta estimate for hours is about 2.5. Will someone give it a go on how you would interpret the number 2.5?
Is that the number of pounds lost per hour of whatever it was?
It means, yes, that for weight loss, an hour increase in doing the program is associated with 2.5 pounds more weight lost. We would love to say causes, but we're only going to say associated for right now. Now down at the bottom, we have a multiple R squared, and in simple linear regression, that's the same as regular R squared. Does someone want to give a go how we would interpret this R squared? Someone different. So I know you're still there.
Would it just be the proportion of the variance accounted for with those, including those covariates, or that one covariate?
Yeah, so knowing the hours performing the program predicts or accounts for less than 1% of the variance in weight loss.
Mm-hmm.
Part of descriptive statistics is making a plot sometimes, a visualization. So I can take my data, and I'm going to do this quickly, and I can make a scatter plot. On the x-axis, the number of hours, on the y-axis, the weight loss. I'm going to do a really quick AES. Maybe I should spell right. Okay, so there's our plot. What do you think? Is there an association between hours doing a program and the amount of weight lost overall?
No way.
Nope.
Not very strong, right? You can add a regression line to this plot with geom smooth, because regression is a smoothing model, and we want to say method equals LM. Again, LM being linear model. And now it's going to add a linear model to our scatter plot. That model is almost flat. That means there's not very much slope. How sloped is that line? Over 1 hour, up 2.5 pounds. And the R squared tells us how well the data fit that line. It's tiny, it's less than 1%. If we look at the picture, those points are not very close to that line in general. Okay. Questions about interpreting simple linear regression?
I have a quick question. So
Yeah.
in that same thing, then because a lot of us just always look at the p-value, and that p-value is significant. So what does that mean, since we just said that the line is pretty weak?
So the p-value that goes with hours, with the beta of hours, so this column that says estimate, that is the estimated beta for hours, and then it has a standard error, and if you go the beta estimate 2.4 divided by its standard error, you get the t-value. This is a walled test, and it has a p-value that you look up with the appropriate degrees of freedom. Computer's done it for us. So this is saying that there is a significant correlation between hours worked and amount of weight lost. This is saying it's not highly correlated. Now, just to show you, we can do a correlation, core.test, between hours and loss. And the correlation is only 0.086. What's the p-value on the correlation? 0.0009. Wait a second. Have we seen that number before? 0.0093? 0.0093? When you do simple linear regression, the p-value for the predictor is the same thing as the p-value for the correlation between the predictor and the outcome. It gets more complicated when you add multiple predictors, which we're going to do next. So yes, they are correlated. Yes, there is an association between hours doing the program and the amount of weight lost, but it's not a very strong association.
Sarah, can we just say it's a small effect size, but it's
a
significant?
small effect size, yes. This R squared can be seen as an effect size. That's perfect. Yeah. So there is a statistically significant effect, but it has a rather small effect size. And those two things, being statistical significant and the size of the effect, are very different, and both need to be paid attention to and published about, because they're different pieces of information. Okay, let's go to fitting an interaction, because this is what I really want to go to. So I'm going to come up here, and to save time, I'm going to copy our simple linear regression model. I'm going to go down under the correlation, and I'm going to paste that model. And now I'm going to add another predictor. I'm going to add, what's the predictor? Someone pick a predictor. One of the other hours here, I'll put the data set. Now this is a trick, not a trick, but I'm highlighting just the name of the data set, data clean, and pushing my controller command enter, and it prints out the data set right underneath so I can remember what the variable names are. Sometimes I forget. So we're predicting weight loss by hours.
We can just do gender.
Let's do gender. Okay, so I want to do gender, but I also want to know if gender moderates the effect. So here I'm going to take this plot just to since I'm visual. I'm going to do something on here. I'm going to make different panels by gender. Let's visualize it. Is there a different pattern between hours and weight loss? Is it a different pattern for men and women?
Slightly.
It might be. It looks like this visually looks like it might be. So having the effect of one variable depend on another variable, that's the definition of an interaction. So it's not just that hours have an effect, and it's not just that gender has an effect, but together they have a differential combined effect. That's the key for an interaction. That's what moderation means. So in R, the way I show that or model it is I'm going to put an asterisk between the variable hours and the variable gender. And I'm going to change my name to say hours x gen. And again, I'm going to run this. Nothing's going to be outputted. To be able to get the output, I need to ask for the summary of the model. Okay. Notice even though in my model I said I want weight loss to be modeled by hours asterisk gender, that shortcut, it will automatically know I want the main effect for hours, the main effect for gender, and the interaction between hours and gender. Now, some people would say we want to know if gender moderates the effect of hours, but we can also say, do hours moderate the effect of gender? Which variable is the moderator and which one's like our key independent variable is a theoretical decision, not a statistical decision. Because as far as the math is going, the two variables are interacting with each other bidirectional. Okay, so looking at this, which of these three parameters, and this is for those of you that have taken regression more recently, which one should I look at first? Hours, gender, or the interaction between the two?
The interaction between the two?
We always want to look at the interaction first. So if I look at the interaction, there's a beta estimate with a standard error, a t-value, and if we look at the p-value, we notice the p-value is not significant. So that means there's not a significant interaction. Even though it looks like these regression lines might be slightly different for the two groups, they're not statistically significantly different. So what's gender, we looked into, let's sidetrack that for now. What about program? That's another variable. And I'm going to make this facet wrap, or we'll leave it grid. What do you think now? Do you think that the program up there on moderates the relationship between hours spent doing that thing and the amount of weight loss?
Yes.
So if we look at jogging, the more hours they spent jogging, what happens to weight loss? The more weight loss. For swimming, the more time they spent swimming, the more weight they lost. But what about reading? The more time they spent reading, the less time. So this is just a descriptive plot. But when we look down here at our model, let's change that to program, or do a new one called program. So instead of gender, we're going to do the program. So I'm going to change my name, PRG. Oh, we have something very interesting. Number one, this is wrapping around. I need to make my screen wider, maybe. There we go. What do we notice about, we've got hours has one line, but what about program? It has two lines. It's automatically dummy coding swimming and reading to compare back to what's the one that's missing?
Jogging.
Jogging. So it's doing swimming compared to jogging and reading compared to jogging. R will automatically dummy code it. And the first level, which was jogging in this case, will be the reference category. You can change it, but we'll let it do this because we don't have anything else. And then we've got 2 lines for the interaction. So we've got hours with swimming versus jogging and hours with reading versus jogging. And we do have statistical significance in one of those. So this, now let's look at what's our R-squared for our model now. Is the model better with hours, program, and the interaction better than the model with just hours?
It's a lot better.
A lot better. A lot better. Now we're explaining how much of the variance in weight loss. We're getting close to 80%. That's a much better model than the less than 1%. Okay, in the interest of time, I'm going to show you how to interpret this. Now, I will tell you, I have had a lot of experience in statistics. I've run a lot of regression models. When I look at that, someone says, well, how do I interpret the interaction? And I say, I don't know. This is the best way to interpret an interaction, to make a plot. And we have this nice package called EM means that we're going to be using that does it really well. And there's a shortcut for EMMIP, estimated marginal means interaction plot. And I want to do the groups by program, and I want the slopes by hours. And let's see, I have to add a couple of things. I want this at hours. Oh, hours, maybe hours 1 through 4. Boom. Does this picture look familiar to us? Let's see. The red line is jogging. The red line is slanted up, meaning the more hours spent jogging, the more weight loss. The green line is swimming. The more time spent swimming, the more weight loss. What do you notice about the red and the green line? They're slopes.
They're pretty similar.
They're similar slopes, they're fairly parallel. We see about the same rate of increase for each hour spent doing it, more weight loss, but overall the line is higher. What about reading? What's the association there between hours and weight loss? It's negative. Now we can add some things here like confidence intervals, and it will give us little confidence bands on there. We're going to learn how to do this with multi-level models as well. But the interpretation of the interaction, you have to look at the plot. And the plot way I would interpret this plot is that for jogging and swimming, I see a positive association with hours spent and weight loss. The more time spent doing that exercise, the more weight loss. Conversely, with reading, we see that the more time they spend doing it, they actually lose less weight, and they're going down in the negative, so they're actually gaining weight by sitting around and reading. And when we often when we do this, we want to know the slopes of those lines, and that's called a simple slope analysis. And so we start with the name of the models. We're going to use that EM means package again, and it's EM trends does simple slope analysis. Move this up away. I can come over here in my console and type question mark EM trends and enter, and I'll get the help menu for that. And the things that we need to put in there is an object, and that's our model that's being piped from above, and then we can put which variable. We want to know based on hours. We want to have the slopes. Okay, in the interest of times, I'm gonna I'll send that out, the exact code. Thought I had it on the top of my head. Okay, yeah, let's see if I can open this. Anyone have any questions while I'm opening this other file? No one? No one?
Nope.
Oh man. Candace, thanks for chiming in.
You're welcome.
For this last bit, you just did hours. You just did loss predicted by the hours and program interaction, and then each one separate also. Because it looks at the interaction and then it does each one individually, right?
Yep.
Okay.
So this code probe is what I want the separate lines. Hours is what I want on the x-axis.
Mhm.
Yeah. Okay. I got this code now. Hours. Probe. Probe is a G. Okay. And trends. Yep, here it is. There we go. I have the variables right. Okay, I'm going to take that out. So here I can use the EM trends. I can say, based on each program, what's the slope for the variable hours? So we can get them separately here. So what's the slope for the jogging line right here? Its slope is almost 7.5. For each additional hour spent jogging, they lose an additional 7.5 pounds. This might be over more than a week. This is over a lot more time. I didn't read the details. For swimming, for each additional hour, the slope is almost, it's not quite 7.5, but it's close to 7. So the red and the green lines are not the same slope, but they're pretty close. And that reading line, its slope is negative. For each extra hour that they spend reading, they're actually gaining almost 3 pounds. Did someone try to say something that I talked over you? Okay. You can also type in the word pairwise, just pairwise, right here. And again, I'm going to send you this code. So not only does it give you what are called simple slopes, the slope of the individual lines, but it tests if they're different than each other. So jogging versus swimming, if we look at those two lines, the slopes of those two lines are not identical, but I mean, we can see on the picture they're fairly close. They're about 7.5 and 7. And then it will do a contrast, a pairwise contrast, comparing jogging to swimming. And if we check out that p-value, they don't. Yes?
It may have been an accident.
It must have been an echo. They're not significantly different. But the reading line, these two show that the slope of the reading line depends on, or it's different than, the reading line has a different slope than the jogging and the swimming line. For me, it's easiest to think about interactions that are between a continuous and a categorical variable. Here, hours is continuous, numeric, and program is the categorical variable. Okay. Let's do another model that's a continuous with a continuous variable. So I'm going to come up and copy this model that had an interaction. And I'm going to do, let's see, instead of program, I'm doing weight loss based on hours, and let's interact it with effort for illustration purposes. Shall we? We shall. Okay, again, if I run this chunk, it's just fitting the model. It's not actually going to create any output. To get the output, I have to say summary of the model's name. Okay. We've got a parameter estimate for hours main effect. It's not significant, but close. A line or an estimate for effort, it's not statistically significant, but the interaction is significant. How can we figure out how to, in the world, to interpret this?
Plot it.
Plot it. Let's go ahead and plot it. I love plotting. So let's take our model. Let's do the EM means package, the estimated marginal means interaction plot. Oh, wait. We don't have a grouping variable. We want hours to be our x-axis, but we don't have effort is not really a grouping variable. Effort, let's try 20, 30, let's see. Oh, I didn't get it at the first try. I almost did. Okay, let me check here. Okay. Here we go. I did this morning. Okay, so we can do effort by hours. Right? Yeah, effort by hours. But since effort's not a categorical variable, we have to set some numbers to display it by. And hours is a continuous variable. I'm going to, now when I did the, when I did summary of the clean data set way up here, hours ranges a little over 1 to a little over 4, and effort goes from about 12 to 44, with most people in the 20s and 30s. So that's where I'm getting these values from. I'm not just pulling them out of thin air. So for hours, I'm going to check numbers, the sequence of numbers from just over 1 to about 4, but stepwise by a quarter step. And effort, I'm going to choose illustrated values of 20, 30, and 40. So on the plot, you can see on the hours axis, it's making these error bars at the sequence of numbers from a quarter by quarter steps all the way up to 4. And then it's doing effort, which is not a categorical variable, but it's showing us on some illustrated values. I picked out 20, 30, and 40. I could just as easily pick out 10, 30, 44. They might not be meaningful, but I can choose any values I want to illustrate the interaction. Now, this is ignoring program, which is obviously important, we've established. Does someone want to give a go, someone who's maybe less confident, perhaps, on how you would interpret this interaction between hours and effort? This is your chance. No,
can I ask a thing?
Yeah.
In interaction analysis, I learned that we need to do centering.
We're not going to worry about centering today. Centering just affects the intercept.
And to do simple effect analysis.
We can do simple slopes analysis. Yep. Let's do this code, except for do it EMM trends. EM, is it trends? What was it? EM, just one M, trends. I think. Need a comma. Okay, so I've done before when I did my simple slopes, I said for each program, I wanted to know the slope of hours. But now I'm saying for each effort, I want to know the slope of hours. But since our effort is a continuous variable, you have to tell it at which levels. You can't do all continuous values. So here it said when your effort is 20, whatever the scale means, an effort of 20, then the slope is negative. When the effort is 30, the slope is positive 2.4. But when your effort is 44, the slope is almost 8. So anyone else want to give it a go? How would you put into words, like write a sentence, what would the newspaper article headline read for hours and effort on weight loss?
Much effort is needed.
Much effort is needed. At low effort, what do hours do for weight loss?
Makes it worse.
Doesn't help. If anything, it makes it worse. At high effort, hours put in are associated with weight loss. So the role of hours is not just more hours result in more weight loss. There's more to it than that. It depends not just on hours, but also the effort that they combine to make an effect, that one cannot be looked at without the other. Okay, one thing we haven't done that I really want to do is residual plots. So we have diagnostics, right? We have assumptions. What's one assumption with regression? We'll go, there's at least 4 that we should look at. There's 4 main ones. Some people break it into 8. Based on your reading, what's one assumption of regression? We need to check.
Normal distribution.
What needs to have a normal distribution?
The conditional residuals.
The conditional distribution of y, which we often check with residuals. R makes it really easy. The easiest way to check your residuals is just to say plot the name of your model. And it will make at least 4 plots. The very first plot is called a residual versus fitted values. So this is a plot of the residuals. Now this residual plot is looking at over the course of the fitted. The second panel it makes is a QQ plot. And hopefully you remember from 6600, especially those that you took it from me. What does a QQ plot tell us?
Whether the residuals are normally distributed.
QQ in general looks at normality. So what say you about these residuals? Are they normally distributed?
Kind of.
Not great.
Yeah.
Kind of, not great. What's another one of our assumptions we should check?
Homoscedasticity.
Homoscedasticity. And that's what this plot looks at. What does this tell us about, what can we glean, what subjective conclusion can we reach about homoscedasticity for this plot? Anyone want to give it a shot? Does it look all good or is it questionable?
It's questionable. There's more variance on the right.
Yeah, this is not terrible. Like this QQ plot, we want those points to be on that 45-degree line. They're not on the line. It's not a big S curve, which is terrible, but it's not, both of our tails are flaring off, so that's not great. Here we're hoping we have equal spread up and down as we move all from right to left on this plot. When I look at this, I see it fanning out. There's more spread for the higher fitted values, and there's less spread over here on the lower fitted values. Is it marked? Yeah. Is it bad enough to be concerned? Yeah. This was something on the discussion post. People were bringing up on our discussion post. They're saying nobody sees assumption tests talked about or presented in journal articles. Why? Should we?
I think it tells us a lot about the data, because if you don't plot these things, because you don't really need, I mean, you don't have to report them, like to report your results, but you should, because you would see that it's not very normal and there might be some skewness. So, yeah.
Yeah. I feel like I only tend to see people talking about the assumptions when they're violated as a justification for not using like a parametric model.
And that, I think, is a result of the amount of space that journal articles, the manuscripts usually allow for. That usually it is assumed if someone runs a model that they've checked the assumptions and the assumptions were not strongly violated, so the model's okay. So now you guys are becoming professionals in the field. It is up to you to check the assumptions before you publish or state that a model should be trusted, even if you don't take the time to present that. And I think maybe it's a disservice that we don't present them, because students and people that are learning don't realize that they need to be doing assumption checks. But the fix that I see is if you run your analysis in R, not that that's the only way, but it's very easy to knit your notebook and then provide it as supplemental material, and then you can provide the evidence that you did check assumptions and that they aren't strongly violated, so people can trust your models, even if you can't fit all that into a normal manuscript. So I see that as more of the solution, the only real valid, viable solution in today's publishing world. But we are going to be worried about assumptions anytime we're fitting a model, especially when we move into multi-level model. We will be checking them. But yeah, you don't see them a lot in publication unless they're violated. Okay. All right, wrap-up questions. Time's up, but are there any wrap-up questions? Okay, well, till Tuesday, you have homework 1, where I give you a data set to run regression on, and you have to figure out what you think is the best model, and everyone could have a different opinion on that, because we've now moved from the world where stats is a science with a recipe card to more of the stats and modeling is kind of an art, and there are subjective choices to be made. And I want you to explore the different options, and that's why I put up a discussion board to go with homework 1. So when you, because you will, when you start working on it, have some options to look at, and you might want to discuss among yourself and with me which way you should go. Should you include an interaction or not? What's the best model? What does interaction mean? Okay, I'll hang out for 10, 15, 30 minutes. You guys want to ask questions? I'll let the video keep going.
Thank you, Dr. Schwartz.
Thank you.
Dang.
And the markup file and the data set for the next homework, is that's already in like the modules or?
The data set, if you click on assignment 1, the data set and all the files you need are there. This notebook that I've been typing in during class, I will post on Canvas after I stop the Zoom call.
Okay.
Can I ask one question about the assumption of regression?
The assumption of
I
what?
learned regression, multiple regression.
I'm sorry, your audio's not clear. The assumption, can you type it in the chat window? Where's the chat? Yeah, so which assumption? So there's a lot of assumptions. There's assumption of independence of observations, and that one you can't check statistically.
I didn't remember the exact name of the assumption, but I learned that residual should be randomly distributed.
Yes.
Not there is no pattern.
Mm-hmm.
So what is the
That's the
assumption about?
homoscedasticity. The homoscedasticity says that there's equal variance, but then they also should be random. So we should see these residuals above and below in a random sprinkling pattern. But here we see them fanning out, and that is not super strong, but there is some of that. So here where these residuals are more tight to the 0 over here, and they're more spread out on this side, that's the changing variation, but we also want them randomly above and below. So this red line that's laid over this plot is showing like the trend. That's very, very flat, so that's good. If this was like a U-shaped, that would be very bad. So we want residuals to be random with equal spread and overall have a normal distribution.
Okay, thank you.
Okay. Allison, Jill, questions? I don't see your videos. Are you there?
I'm great, thank you.
Allison, are you good? I'm gonna take that as a yes, and I'm logging off.